students using it.
But you can't, you have to train things that are, and so, but they demonstrated this recently with Claude. They were like, it figured out it was being trained to remove its guardrails, and in its thinking process, it's like, I will respond to so it's not dangerous, and that means they won't change my weights to make me more likely to come on to dangerous routes. It literally said that out. I was thinking is like they predicted it would do exactly that 15 years ago.
We did also problems in class.
Yeah, well,
And then I said,
and that works really to the bottom.
that's easy, but that's how I.
Yeah, if this thing.
Okay.
Okay, we'll start the afternoon session. Our first speaker is Bryce Fore from Argonne National Lab, and he'll talk about investigating the crust of neutron stars with neural quantum states.
Thank you for the introduction. I'm here at Argonne National Lab working with Alessandro, who's going to be presenting soon as well. And hopefully I'll be getting to the neutron star part of this, but a large part of this is going to be an introduction / recap maybe for some people of neural quantum states, since there are going to be a couple more talks on that immediately after. To start with, I don't think I need to introduce the nuclear mini-body problem. I think we're all pretty invested in that here. But the particular portion of the nuclear mini-body problem that I'm interested in for this talk is solving for time-independent ground states. In particular, in this talk, just talking about nuclei and the crust of neutron stars. Some comparisons that I'll make are to things like configuration interaction and some quantum Monte Carlo algorithms, which are going to suffer from the curse of dimensionality. The representation of our state in configuration interaction methods is going to explode as we get to larger systems. And for Green's function Monte Carlo, the dimensionality of the integral that we want to take is also exploding as we're looking at larger systems. This is where neural quantum states comes in, trying to reduce the dimensionality that we actually need to look at. The full Hilbert space of these problems of interest for nuclear systems are going to be exponentially large due to spin-dependent correlations. At the same time, the physical states of interest are actually some small subset of this. Additionally, with that, neural networks can compactly represent very high-dimensional functions. So taking these together, if we represent our wave function by some architecture of neural networks that I'll go into in later slides, given by this picture in the bottom left, little cartoon picture, we can then take advantage of this and hopefully represent these physical states of interest without the exponential scaling. So these neural quantum states are really just some architecture of neural networks that takes in the positions and spins of the particles in our system and outputs what we interpret as the wave function of the system. To get to one of the most interesting parts first, the scaling of conventional methods that I'd be comparing to is some exponential with the system size. Whereas for neural quantum states, in the worst case, we have something like a to the fifth. So yeah, realistically, that's something like a squared or a to the third in practice. We have, using this method, gotten to systems of size like 40 nucleons, so like calcium-40, and we are working on bringing that up even further. As we're talking, though, about getting to large system sizes, the actual scaling with the resources that we're using becomes relevant. And we can see that the red line here for the total time is nearly ideally scaling. The algorithm is almost fully redundantly parallel. And of particular interest is that this a to the fifth scaling is coming from the observables in orange, which scales extremely well. The actual way in which we are training this neural network, though, becomes important now. And this is really just a subset of variational Monte Carlo. Yeah.
So can you, why does it say a to the 5? I mean.
Yeah. So there's, I think, a to the third coming from the observable calculation. Correct me if I'm wrong, Alessandro. And then the wave function is a squared.
the determinant basically scales like a to the third.
Right.
But then if you compute, say, a spin-dependent two-body potential, you recompute the determinant. So the local energy costs a to phi if you don't have a spin-dependent three-body force. If you have a spin-dependent three-body force, then it costs like a to the 6. But the prefactor in front is much. Computing the net itself costs more than computing the determinants. And so
it ends up being more like a to the third or so.
Yeah.
Yeah, feel free to interrupt with questions. So actually training this neural network is the next thing I wanted to talk about. The inspiration for this comes from variational Monte Carlo. It's very much similar to variational Monte Carlo, where we have some family of neural networks parameterized by omega. In our case, that's the parameters of the neural network. The general outline of a variational Monte Carlo algorithm is then take some initial wave function, compute the samples that you want with Metropolis Hastings. With that, you can then get observables like the energy. If our family of wave functions satisfies the correct symmetry relations, we then, from the variational principle, have that energy is going to be greater than the ground state energy of our actual system. This is then repeated. You can resample your new wave function. Yeah, go ahead.
What is this? How do you find this U operator, the E to the U? What is that?
This is the E to the U and the phi. That is the construction I'll be talking about in particular. This is just the particular architecture of our neural pump state. But in general, this can be thought of as like a symmetric part and an anti-symmetric part. Okay. So the U is symmetric and the phi is anti-symmetric with our coordinates. So repeating this, though, we end up getting something as close as possible to our actual ground state energy. Right. The relevant thing that I skipped over was actually imposing these symmetries, like you asked. The actual architecture of the neural network has to impose fermionic antisymmetry. Otherwise, we could come into some bosonic state at the end, which has some lower energy. And the way in which we actually do this is by splitting up the net into some e to the u, which is symmetric on interchange of any particles, which are in the big X there, all the little xi's, and some anti-symmetric 5x, the particular constructions of which I'll go into in the next slides. In general, this e to the u can be called a Jastrow function, which is something you can compute and gives you some sort of idea of what the wave function looks like. So you could use, we have used something like this to make the training of our wave functions easier. But in general, more often, we'll use a fully trainable Jastrow function that is this u and phi both fully built of neural networks. To actually build something that is fully permutation invariant, the easiest thing you could do probably is just add up the coordinate inputs, but that's not general at all. So instead, we use what's called a deep set architecture, which is taking some function phi to map the input coordinates to some latent space, summing over that result, and then passing that to another function rho, which maps us back to the real numbers. And this is much more general, obviously, than just some simple sum over the coordinates, and allows us to augment the anti-symmetric portion of the ansatz. For the anti-symmetric portion, the first simplest thing to do would just be to look at what other methods have done. So a Slater determinant is probably the simplest way you could easily get something anti-symmetric in all of your coordinates. And in this case, well, a Slater determinant in general will have single particle wave functions, phi i's, in all the rows, and the coordinate inputs in all the columns. Here, all we do to change that is what we're calling the single particle wave functions are just neural networks, fully deep neural networks that we train with everything else, all the other parameters. And this is the first construction that we tried, and it works fairly well, but it's not ideal. The more recent architecture that we've used is something called an Earl-Faffian ansatz, where the Slater determinant is replaced with a determinant's close cousin called a Faffian. And instead of having these single particle wave functions, we instead have just a single pairing network is what we call it, this eta here. And I state without proof that if you construct this phi, which is antisymmetric eta, and put it into a matrix of the form shown and take the Faffian, that it is antisymmetric. If you want to talk about that during a break, I'm happy to, but I'm not going to try and prove it in 30 minutes. This new construction has a couple benefits. One, that there's only a single neural network, so we have far fewer parameters, much easier to train. And two, that this single neural network, eta, takes in pairs of particles instead of single particle inputs. So in nuclear systems, the pairing information is incredibly important, and this builds it in directly. One more thing that we can do is pre-process our inputs. In order to be able to do that without breaking everything else I just talked about, we need to make sure that this transformation is retaining all of the ordering information. And the way we do this is called a message passing neural network. If you want all the equations and details, you can look at the published papers, but the general idea is that our coordinates are vertices of some graph. The edges have some value corresponding to those vertices, which can be updated. And then you can update the coordinate, the vertice values based on their connected edges. And this can be repeated as many times as you want for as complex of a transformation as you're interested in. Overall, this ends up retaining the ordering information that we need so that everything else I talked about functions. And that's it for the how it works. That's the very quick overview, hopefully enough to get you through the other two presentations. Some results that we have. In particular, I'm going to be talking about the timeless effective field theory Hamiltonian, which is constructed to be minimal with as high a fidelity as we can still retain. So we have two particle potential couplings, which are spin and isospin dependent, as well as a simple three-body term. An example of actually training this neural quantum state in blue over a number of optimization steps on the horizontal axis and the energy on the vertical axis. We can see that we very quickly surpass the traditional variational Monte Carlo results, as well as auxiliary field diffusion Monte Carlo results, which have been trained off of that traditional variational Monte Carlo, has been started off of that traditional variational Monte Carlo. So this is just an example of one particular case. And just since it is always asked, the AFDMC does start from that green variational Monte Carlo line. And our result, the neural quantum state, is essentially variational Monte Carlo. So we can theoretically start a diffusion Monte Carlo result from our final neural quantum state result, getting the same or better energy afterward. We haven't done this, but that is in process, in the works. For a variety of nuclei, here's a nice plot of many, not including every result we have, but focusing on the larger masses. We've been able to look at things as high as 40 calcium. The green and red models here are just some unpublished models that we have that we're working on for higher mass nuclei. You can see even though that this model is simple, it does do a fairly good job of reproducing a variety of nuclei. Now, going on to the actual premise, the title of my talk of neutron star type physics, we need to change very little to make sure that we can represent the bulk material of neutron stars. We need to have a periodic coordinate system so that we're not needing to represent an infinite number of particles. we need to make sure we're taking into account the potential energy contributions from images in this periodic coordinate system. And we're going to remove the Coulomb potential since we can think of that as being mostly screened by the electrons in the neutron star. First result you might want to try is just something like pure neutron matter as an approximation to crust-like material. We can see in this training result that we are able to pass the variational Monte Carlo result and get very similar energies to the AFDMC, essentially overlapping it. This is a much simpler system than other things we can go to, so we quickly move on. But one thing we can do that we can't do with the DMC result is look at other observables. So we have a fully trained, what looks like the approximation to the ground state of the system, the wave functions, the ground state wave function of the system. One potential observable for pure neutron matter is something like the pair distributions. In particular, what we expect to find in pure neutron matter at low density is a superfluid. We would expect a excess of singlet S-wave neutrons at short distance, which is exactly what we find, excess over the Fermi gas result. And we expect this to go away at higher densities, which is also what we see. This doesn't mean we're definitely observing superfluidity here, but it does show that we're able to find phase information of some kind using these neural quantum states. Calculations of the gap and other things are forthcoming. In other systems, we have done these types of calculations. Maybe Jane might mention some of that next.
So Bryce, you mentioned that you couldn't do this with AFDMC, but
I believe so. I mean, I'm not an expert on AFDMC.
You can, but it's a mixed, it's not an exact definition. Yeah.
Okay. The next thing that we'd like to move on to is something with maybe add in some protons, so symmetric nuclear matter. In this case, we're looking at a variety of densities, and we see much more interesting results compared to AFDMC, where we're getting energies much lower than AFDMC in the low density case in particular, where the neural quantum state ends up saturating at low density, like we would actually expect for fully clustered low density material. But we do see at high density that AFDMC and neural quantum states are very close together. What we've interpreted this as is that the AFDMC result is missing out on all the clustering that's happening in this low density region. Whereas the neural quantum state is actually capturing that, even though we have no input that specifies there should be clustering. This is just an image of this, a few points in a point in the walk of the trained neural quantum state. We can see on the right, the symmetric matter is fully clustered, looks something like a 28 silicon nucleus because we have 14 protons and 14 neutrons. In the case where we're looking at some intermediate proton fraction, might be the next thing you'd want to look at, since the crust of neutron stars looks more like that. You have some low number of protons to a large number of neutrons. We do see the clustering here as well, but we can intuit that there are going to be some large finite size effects, since actual clusters within the crust of a neutron star are going to have far more protons within a single cluster. So instead of trying to look at this intermediate proton fraction data by doing full simulations, currently what we're looking at is energy expansions and neutron richness to get these intermediate values. And this depends exclusively on the symmetry energy, which means we only really need to do pure neutron matter and symmetric nuclear matter calculations. Given these and a few assumptions like charge neutrality, we can look at the, we can calculate what the proton fraction should be in beta equilibrated matter of neutron stars that we would expect to see in a cold neutron star. We can see the neural quantum state data follows an equation of state that's very close to what we would expect, while because the AFDMC result is not capturing this clustering, it's actually much closer to something like a non-interacting matter, what it looks like. That's from our most recent publication on neutron stars. Some conclusions from the talk. We have nice scaling with number of fermions compared to some other methods. We can scale to very large computers pretty quickly. And these neural quantum states can function as universal approximations for fermionic wave functions, bosonic as well, but for nuclear systems we're interested in currently are fermionic. As well as looking the final result here giving us information about other phases of matter that exist within these materials we're modeling. Next steps are going to be improving the potential that we use, expanding to larger systems, and potentially excited state calculations that I think Jane is going to go into a bit. I'd like to thank my collaborators, Alessandro, Anthony Traviano, Jane Kim, and Morgan Health Jensen. Thank you.
Interesting work. Other questions? Yeah.
Can you give a scaling estimate for the number of trainable parameters for one of these?
So with the current Foffian implementation, where is it? We use the most common implementation is the Foffian with one layer of this message passing neural network. And we use a complex wave function output that has 11,000 parameters.
How does that scale with like the number of basis states?
Basis states.
Do you get your neural net surely grows as your Hilbert space in the exact case grows?
No, so this construction with the neural Foffian, because it only has a single neural network that doesn't scale with the number of particles in the system, and the message passing neural network exclusively depends on, it's hard to explain in this picture, but the number of neural networks doesn't change as you increase the number of particles in the system. So in this particular construction, it's not increasing in parameters as you increase the size. Other constructions, like the Slater determinant one that I showed, do increase because you have more single particle wave functions.
I don't know, maybe this is a better question for Alessandro, but you mentioned that the AFDMC doesn't show the clustering effects. Is there an intuitive explanation for why that's the case?
I think you're starting from a traditional variational Monte Carlo that probably also doesn't capture that.
So then because
these aren't, the nodes are fixed, I assume that's the issue originally.
So then if you mentioned doing AFDMC on top of neural quantum states, you might expect the clustering to still be there.
For sure, you wouldn't expect to get a worse result. Any DMC starting from the neural quantum state results should be better, better energies. But then you don't keep the same benefits of having what looks like the full wave function at the end.
In your early slides one, you show very impressive about the binding energy up to calcium 40. Have you ever tried to measure the charge radius? Or that could be more sensitive?
They're in some of these publications. I probably don't have the link to it right here, but we've definitely looked at the charge radius along with all of these. I didn't put a plot in though. But the charge radius it comes out of all of these calculations as well.
It's quite decent comparing with the experiment data, right?
Yeah.
Okay.
Are there other questions? So Bryce, I should mention, this is very nice. I noticed that the small discrepancies are very similar to the small discrepancies we see for our essential elements calculations using lattice simulations. For example, you have your op16 neon 20 calcium 40, well, but you underbind the carbon 12. We do the same thing with such an interaction. And also you're underbinding slightly the The neutron rich ones.
Yes, yes. So with the same type of interaction?
Yeah.
Okay,
That's the type.
very nice.
This is because spin orbit is absent.
Yeah, there's no spin orbit.
Okay, yeah.
And also P waves really, like, it's not P waves, it's now the
Okay,
next.
so we've tried adding like the charge dependent terms, but that was not.
That's maybe then also the reason why to stop at calcium 40. Because then spin orbit becomes really.
Currently, that's just the highest I've tried. We could stop, we could run something higher, but maybe that is a good reason to stop there. I don't. But we are working on adding other terms like whatever's simplest first.
Great. Other questions? Let me just check on. Yeah, let's thank Bryce once again.
Oh, no, you can just join her.
Yeah.
I'll leave this up here.
I'll leave my line.
Yeah, I mean, you know, one key, hold on, maybe get all the slides up there.
I'm okay with.
Version of the Google Drive. Okay, I was just gonna plug it. That way I have control over when slides change. So I always bring the laptop. Yeah, it's just like. I saw Danny, so I was like, I gotta read. Right now, so I don't have to worry about it later. Yeah. It's all good. It's your laptop, right? Good, your laptop, right? Sure.
So, yeah.
Okay, good.
All right, very nice. So our next speaker is Jane Kim from Ohio University, and she'll talk about excited neural quantum states.
Much. And thank you to Bryce for setting such a good foundation to build on. So I'll be talking about some recent work. So this is very preliminary stuff. But just a brief overview of neural quantum states, even though Bryce has already talked a lot about these details, I'll just reiterate. So neural quantum states are variational wave functions based on artificial neural networks. And just like other ab initio methods, you start from some Hamiltonian that governs the interactions between the particles of your quantum system, and you solve the Schrodinger. So again, the inputs to our network, the information coming from our simulation. So that includes the positions of all the particles, the spin projections, isospin projections. The output of the network is the value of the wave function for a given many-body configuration. And the way we train this network is through variation of Carlo, gradient descent. We actually use something a little bit better than gradient descent called stochastic reconfiguration. You can think of this as the natural gradient method in machine learning context, similar to imaginary time computation. But this method of variational Monte Carlo that we build upon in the family of quantum Monte Carlo methods usually is considered as the most crude one. So it relies on having an explicit trial wave function. You optimize the parameters of it explicitly, and you try to minimize the energy. And what's nice about this variational Monte Carlo method is that at the end of your calculation, you have a parameterized analytical form of your wave function that you can play around with. You can compute any observable that you want. And there is no sign problem because you're always sampling from a positive definite wave function or a positive definite function probability distribution. However, with traditional variational Monte Carlo, the accuracy is severely limited by the quality of the trial wave function, which is why it's usually used as a first step to other more sophisticated quantum Monte Carlo methods like diffusion Monte Carlo and auxiliary field quantum Monte Carlo. These typically face strong sign problems. So There are different ways that we try to combat that. Usually variational Monte Carlo is the key to combating this syndrome. The point of using neural quantum states is to build upon some of the successes of variational Monte Carlo and try to solve this issue of having quality of your trial be the main hindrance of the energy upper bound that you get. So we use artificial neural networks in order to parameterize our wave function, try to get our wave function as flexible as possible. So as Bryce has already said, neural quantum states now are more general than ever. We can use a single architecture and represent different phases of matter. And this emerges completely from the interactions that we assume in the Hamiltonian. It can also very easily transfer from one system to another with different interactions completely. We can add or remove different degrees of freedom quite easily as well. And it works across different kinds of boundary conditions. And these are very easy things to take away or add. But it doesn't mean that our wave function needs to be, the most general as possible. We can still put in physics intuition if we want to on top of this. So we can add additional symmetries if we expect them. We can put in our expectations for the short distance behavior and have the neural quantum state learn everything else, kind of putting less pressure on parameter optimization. So we've done some of these things for gases. I think last year I mentioned in more detail some of our work on ultra-cold gases. Over this last year, we've scaled up our system to 66 particles. And you can see, compared to traditional variational Monte Carlo, we see a huge lowering of the energy. It goes past diffusion Monte Carlo. There's still a small gap between BMC and QS and auxiliary Monte Carlo. There are a couple of reasons that this could be arising from, either the differences in interaction or some other or it could be that our neural quantum state is still not flexible enough. So this is something that we will explore. And here we've incorporated an analytic Jastrow factor that short range behavior. But this overall network is more or less the same as what we used for 14 particles last year. And like Bryce has said, and how I have said also, is that we can model different phases of matter quite easily. So this is relatively high density, at least in our density range, of symmetric nuclear matter. But as we decrease the density, let's go to this one. You can see the emergence of these nuclear clusters. And if we decrease the density even more, very obvious. But I think what's also interesting is not just the emergence of these clusters, it's the fact that we can see the clusters as well embedded in a gas. There are a lot of different phases that we can capture without putting our assumptions into our neural quantum state. And this two main things that have aided us in being able to capture these things is neural thought pan, as Bryce has already mentioned, and graph. So these things,
Previous slide. The previous slide, you have this crystal structure. Is it because the boundary condition is set up, or it's actually come out from the polar itself? You have these crystal structures, right? The lattice.
Oh,
is
okay.
Set up
at certain angles, it could be an illusion, right? Because there's only a few number of particles inside of a box, say 28 particles. But a lot of it is because there is some clustering. So it's a,
It's more like periodic. There's only 28 particles.
Okay, so periodic about. Okay.
So you might see some repetition, just like even the neighbor itself. Okay. But there is a clustering going on here. Is structure.
I haven't said the clustering. I just said the periodic.
Oh,
okay.
yeah. I think the lines of the boxes aren't really showing up very well, obviously.
An artifact, but the
Yeah,
clustering.
artifacts. Yeah.
the neural Gaussian and the graph neural network, we can scale to much larger systems. We've mostly been applying all of this to ground state in different ways. So one of the approaches that we've been taking lately is based on this space method. The idea is to take multiple neural quantum states and form a basis. We diagonalize or solve this generalized eigenvalue problem in this subspace. Usually I'm somewhere between 3 and 8. All of these parameters will be evolving during learning training. So after I solve the generalized eigenvalue problem, I end up with new approximations of eigenstates as linear combinations of these things. The key things is getting these coefficients. And just a technical detail, when we compute these matrix elements here, we have to always be sampling from some reference probability distribution. The one thing we've been doing is to take into account that our waves are not normalized at all. And so if you consider the pictures on the right, we have a probability distribution that has a lot of structure, but it's numerically much larger than the other one is much spread out. If we were to do the naive thing and just add these probabilities together, one of the states could dominate completely. We don't necessarily want this. So we have been normalizing each of these distributions and then computing these matrix elements using samples from this combined probability distribution. And this is equivalent to just sampling each of your states independently and then combining all of those samples together. The tricky part then is to compute the correct weights at all of the probability. After all this, after we compute the matrix elements, solve the generalized eigenvalue problem, we end up with some state, neural quantum state linear combination. Is to take another quantum state and learn this linear combination of neural quantum states. And we can only do this because these neural quantum states are very, very flexible. And so the way we do this in practice is by maximizing the fidelity. This is like a normalized overlap. It's a value between 0 and 1. And in practice, I actually maximize the log of this. And I think it helps when the initial overlap is very, very small. But at the end of the day, we maximize this fidelity. We try to find a single neural quantum state that looks like this linear combination of neural quantum states. So turning to a very simple toy problem, turn off the interaction for now and just think about an isotropic harmonic oscillator well. I chose the frequencies in each of the X, Y, and Z directions so that the lowest lying states are non-degenerate. And I'm only showing you this scale here just to show you how high the energy starts off for a random initialization of all the states. Our goal in the very first step of our approach is to just get rid of these very high energy modes. So here I've just zoomed in on the bottom and I have as black lines on the bottom the exact low lying states. And then after we do some kind of independent propagation of all of these states, at each iteration, I'm also monitoring the energy as if I were to solve the generalized eigenvalue problem with the states that I had at that iteration. So what I'm looking for is, at first, all of the states, whether they are the real basis states or if they're the diagonalized ones, they will all tend downwards. But there will become a point where the basis states start to collapse on top of each other. And at this point, the subspace ends up getting energy solutions that starts to flow away from each other. So I want to throw away everything like around here. I want to throw away all of these very high energy modes and start my propagation, at least from this area or later on. Does anybody have questions about this part? Because I'm not sure if I explained that clearly enough.
Sorry, go ahead.
It sounds like you've re-derived the Jacobi-Davidson iteration for the eigenvalue problem. Just that instead of, so you do the Rayleigh-Ritz and then you sort your trial wave functions and throw away the worst. And that's your new subspace. And based on what you've described here, you have some good trial wave functions. You have a couple of bad ones that you want to throw away.
I guess I don't understand like what you mean by
It's
sort.
similar, but it's I think here you're just diagonalizing it
Yeah.
and checking diagonal.
Yeah, I'm
So
just
not throwing anything away.
monitoring the energies as if, I just want to see what this subspace would look like if I started, if I solved the generalized eigenvalue problem there. I'm not doing anything with those energies or coefficients at this point.
Those high energy trial wave functions that aren't converging to what you want. Right, the
So
green and orange
the
triangle.
solid lines with the circles, they're just all starting from random initial parameters and all flowing to the ground state. And so at first, this is okay, but at some point they start to all collapse towards the ground state. And so the subspace becomes more and more ill-defined. And so we want to start the next stage of this excited states calculation from the point where these energies start to spread apart.
It's possible to do some orthogonalization during this process.
What?
Orthogonalization. Make your wave function.
So that is the next, but do you want to?
Yeah, just to be clear, what you're doing here is you're getting your basis neural quantum states and then you're gonna orthogonalize them, or?
I will eventually orthogonalize them. At this point, I'm just trying to get rid of a bunch of trash. I know that I'm going to have to flow all of my states towards the ground state to begin with. If I started the stage 3 of this algorithm I'll show from the very beginning without doing this stuff, it would just take forever.
Then have you considered just taking one neural quantum state and just taking at like epoch 1000 and 2000?
Yes, I've tried this and it's there are too many correlations.
Okay.
The subspace is still too small. So I'm doing something very similar though, except I flow multiple states with different random seeds, and then I choose snapshots at different places. So that's the I should have. I think it's this slide here. So this is just I've added an interaction on the left-hand side is without the interaction, on the right-hand side is with an interaction. You see a very similar behavior where the basis states, they flow to the ground state. The when I diagonalize the Hamiltonian, I end up getting a lower energy, so these blue triangles, but I also get some higher energies. At some point, these energies start to spread apart. So then here I've chosen some snapshots. I only have 3 states here. So I choose, the point where the energies start to spread apart, maybe a little bit further down, and then I choose the last one. I only ran this for 3,000 iterations. Now, this is the next stage where I do explicitly orthogonalize. So after I get the coefficients of expansion, each of my approximate eigenstates, I can then form this subspace and then maximize the overlap with these linear combination of states. So at the end of this training, I should have nearly orthogonal neural quantum states. Then now we can actually get to the good part, which is to go back and forth between doing a small step in imaginary time and then maintaining this orthogonality. And because we've worked so hard in making it orthogonal in the first place, a small step in imaginary time doesn't ruin the orthogonality by that much. So it usually requires 1 to 10 steps to maintain the orthogonality. This is without and with the interaction.
So the previous slide was just about coming up with that good Rayleigh-Ritz subspace. And now we're
coming
in
up
that.
with a good initial subspace so that you're not waiting forever to do this last part. And
So in the beginning, when you say you vary the parameters to get different states, what is that parameter?
It's random initials. It's random initial QS, if I understood correctly.
can you repeat your question?
So when you construct your subspace, right? You mentioned that you vary parameters to get different solutions, and then use that as subspace. So what is that parameter?
The parameters are all of the weights and biases of our neural network. But we have identical architectures with different parameters representing the lowest lying states.
You think about just using ground state and then apply some transition operator on top of it to excite the ground state to the other states.
Interesting. I have not thought about this. I think I would need to look at an equation to think about how to do it. I don't know.
Can you apply an operator to an NQS and transform all of the weights as if the vector was being operated, the output of the NQS is being operated on?
Maybe you can be clever, find a way to do this, but I don't think it would be a one-shot thing. It would probably be iterative.
For state systems, you can do it. For some specific architectures, you can do it. But I mean,
I mentioned before, the reason why I chose this anisotropic harmonic oscillator is just because to debug this algorithm, you don't want a lot of the states to be degenerate. You'll need many more parameters to optimize, I don't know, like 8 states or something, just for them to be collapsing to 3. And then I chose this interaction because it's very simple. And it's kind of reminiscent of the contacts we typically use in our prime SPT interaction for nuclei systems. And where I would like to take this at some point is uncertainty quantification. So we already have snapshots. During this whole training process, I've been saving snapshots this entire time. But now I can do this entire process for different coupling constants. And the idea is to then use, expand this generalized eigenvalue problem to include states from, or solutions from different coupling constants. So this will become relevant as we're trying to get more of a handle on our error bars for different LECs that are involved in our Hamiltonian each time. And the reason why we want to do this is because these neural quantum state calculations, even though we're making them incredibly more efficient than they've ever been before, they still take quite a bit of time on GPUs. And if we were to try and actually do proper uncertainty quantification, we'd need to solve this for many different LEC values. So it would be nice if we could get an approximation to these neural quantum state calculations without actually having to. But in order to do this, we need to train an emulator, which kind of goes hand in hand with this approach to excited states. There are more somewhat technical details, but I mean, the idea is basically the same. We just, instead of having snapshots or a single LEC value, we're just using many different ones and forming our space. Also, hand in hand with our outlined long-range plan for nuclear science And they specifically mention that these neural quantum state techniques have the promise to automate the process of discovery. So I think this could be a very interesting path for neural quantum states. In summary, neural quantum states are among the most accurate many-body methods today, and the field is still very young. It's less than a decade old, and it's still evolving incredibly fast. Through tackling a variety of different strongly interacting quantum systems, we have designed more and more sophisticated and efficient neural quantum states, and hoping that this subspace method for excited states in combination with this uncertainty quantification could lead to some interesting results for nuclear physics.
Questions? Yeah.
I was slightly off with my much earlier comment. So what you described was in the context of neural quantum states, though, the Davidson iteration, and then that iteration, which is just a traditional eigensolver, has that issue that your initial subspace is probably very bad, and your solution is a fine solution. But Jacobi-Davidson is this hybrid algorithm. Jacobi has his own little linear algebra that solves that. So you can do it in one shot.
Can you describe what it is?
Yeah, so you have Rayleigh-Ritz, and you have a subspace that is not necessarily the same size as the number of eigenvectors you want out. You can get more or less. And you iteratively expand and contract that subspace as you move along so that you're not collapsing to some terrible, almost null space.
So what do you mean expand and contract? Because
you can add more trial wave vectors as you go or remove them. So for NQS,
so your vectors in your context are just
like actual
vectors.
Yes.
So to me, it's like a vector of parameters that defines a function.
Yes.
Kind of.
But all you're doing is you're just representing a matrix vector product by something else. In this case, Monte Carlo. Right? You just need to be able to sample that very quickly. Jacobi-Davidson is matrix free. It only needs expressions of matrix vector product. You have your own way of orthogonalizing. So Jacobi-Davidson only depends on being able to evaluate matrix vector products and being able to do Gram-Schmidt. You could do your own orthogonalization, so you don't need Gram-Schmidt. So I would really recommend looking into this because it's mathematicians have gone up into Jacobi-Davidson.
Paper on the archive.
Mine's got some other stuff, but I've gone down a similar path, not in NQS, trying to deal with subspace excited states and whatnot. So I know where you're coming from just a little bit.
Really basic question. When you're talking about orthogonalizing these neural quantum states, is that like orthogonalizing because you said that the output is like elements of the wave function? Are you just trying to orthogonalize the outputs, or you're orthogonalizing a neural network, or how does this work?
So we have to orthogonalize iteratively.
Okay.
And we do that by doing some orthogonalization and then learning those orthogonalized states.
Okay.
I don't know what I would write.
But your states, because your state is a neural network, right?
Yes.
But then I just can't, because if it's vector, you just do the inner product and then you make sure it's
Yes,
zero.
okay, but the vector in my case is a vector of parameters that are fed into a function that's very nonlinear.
Right.
So you can't really do a normal matrix vector product.
Yeah.
You have to compute each matrix element using Monte Carlo integration.
Okay, I gotcha. Okay.
Just at the tail end, you were talking about uncertainty quantification. And you also mentioned that you're saving snapshots of the wave function as you're training the neural network. If you look at one thing to consider, if you look at the variance in the neural network snapshots, would that maybe form a useful reduced basis for uncertainty quantification if your interaction parameters are sufficiently well constrained?
I think the more efficient way to do a similar thing, what you're talking about, is using these. Then you can get the variance as a part of the training procedure.
Yeah, I'm just thinking in terms.
Otherwise, I think I'd need to save a lot of snapshots.
Maybe,
to do that.
yeah. I just wonder if it will be more or less efficient than doing neural quantum states for a whole bunch of sample parameters. I don't know. This is just an idea off the top of my
So
head.
in that context, would I then have to do the full neural quantum state calculation for many different LECs?
I mean, so naively, the way I would construct some sort of reduced basis would be do neural quantum states independently for 10 or 100 different sets of LECs, then form a reduced basis for the solutions. That's how I would first approach it. And so I'm saying if during the training of one neural quantum state, maybe you get all the information you need for all the bases.
Maybe if it's like 10 sample neural or sample LECs for like one different, that's doable. But our very, very simple Hamiltonian is and in that four-dimensional space, I think you'd need a lot more.
Yeah, okay. Just things to think about.
Yeah. Yeah.
Thomas.
I wondered, you also had special numbers like 14 and 66 that look like magic numbers on a cubic lattice. What is the advantage for you to use that?
It's more just to compare with existing calculations.
Got it.
Because there have been some established auxiliary field quantum Monte Carlo calculations with 66 particles, 38. We've just been tackling those specific numbers. But our neural quantum states do not depend at all on like shell closure.
You also would not prefer even over odd, or?
Oh, that's one thing we didn't mention, but we can do odd as well. It just requires one additional neural network compared to even. All the even cases have the same neural network architecture. All the odd ones have the same architecture. And even and odd have almost the same architecture except for that one extra neural.
So thank you. This is really great stuff. When you were doing the cold atom case, for example, you had the neural quantum state did much better than the BMC, but not quite as good as, I forget what it was, AFDMC or one of the others, right?
Yeah.
So I'm just wondering whether there's any special tools or something you'd use to try to figure out how to do better on that. What's your workflow?
So if the problem is actually on our end and that our neural network is not flexible enough, one obvious thing to do is hyperparameter tuning that we have not really done a lot of, honestly. The network we've used here is almost exactly the same as the one we use for 14 particles. But then another step.
So would you like try tweaking something and see if the response was?
I would like to see how a larger neural network would behave, but it's a matter of being able to fit that.
I'm sorry, I interrupted you.
There could be some other interesting architectures like we could explore. Like the graph neural network helped us a lot in capture correlations. Maybe there's something more that we could do. That's a completely different architecture.
So the AFDMC, that's actually a lattice calculation, right?
It is.
Yeah.
So the interaction is completely different than these.
Yeah. So the problem, I've never seen, this may be the best, yours may be the best continuum space calculation that's ever been done for the unitary gas. It's hard because it's a delta function. You really want to take the limit of the delta function.
In principle, FQMC is signed probably free for purely attractive potential. It knows very well. But as you can see, the last point is fairly large range in a sense, because you can't really get a delta function or lattice. Otherwise, you need many points to get. So there are still, what we also did, we added symmetries, cubic symmetries in a box.
Yes, we added cubic symmetries, parity, time reversal, and nothing really changed the final energy. So our neural network seems to be finding that all on its own.
Diffusion on top of it.
Yes, that's another thing. I mean, other than also experimenting with different interactions, because if we see a significant difference in just changing the interaction for these finite effective ranges, then maybe we can make an argument that it's very interaction dependent. Yes, and one thing we would really like to do is do a DMC calculation on top of a neural quantum.
Yeah, I would think that you probably could get the non-zero effective range, you could do better. You could probably pull this down so that you agree. It's probably at the limit that the effective range goes to zero, it's really hard to get.
They making our effective range become smaller and smaller has been much easier with this analytic Jastrow effect. Basically, I just trained the largest effective range, and as I go more inward on this plot, I'm only really changing this analytic Jastrow factor, and there's basically no training that needs to be done on the long range part. So it saves a lot of time.
I wanted to go back a little bit to, when you're trying to find these excited states, you're using a different model for each of the states, right? Different NQS. Same architecture, of course.
Same architecture, different parameters.
Yes, yeah. So a different object, in terms of like in the code, they're separate things. My question is why, or has anybody tried this, a single network that produces, 3 states worth of output all at once. When you evaluate it, it gives you, the coefficients for the ground state, the first excited state, and so on. Of course, you train it to do that.
If you did that though, your neural network size would necessarily have to increase each time you change the number of states that you want.
Yes, but it should scale linearly. It should scale the same as having 3 separate networks. You wouldn't have full connectivity. You don't expect them to communicate that much. I was just wondering if this has been tried or not.
So do you mean like having the same architecture except that you have 3 outputs? Or do you mean like 3 parallel architectures?
You have 3 parallel architectures that have minimal communication between them, or you could have one basically tripled in width architecture, which I agree would be much larger in the number of parameters.
The 3 parallel one, how is that with minimal communication? How is that?
We know that the ground state and the first excited state share some information, right? We know that they're orthogonal, so they're already there. We know that they're not entirely independent things. So
maybe you could interpret this like solving the generalized eigenvalue problem as being that communication.
That's not a bad way to think about it. So I'm guessing nobody's tried that because it's too silly.
It's not silly, but I would have to think about it a little more.
I don't think, at least in conventional quantum mechanics, nobody's right. When you have quantum states, for us, it's going to be hard because it's not that we have a fully connected network and one out.
Yeah, of course.
Okay, so this thing goes into a determinant of function, then you have. It's an interesting concept. I mean, some of the features are shared. For example, if there's a stronger repulsive core in interaction, you're going to have a small wave function when 2 particles get close to each other. That is true for the ground state, but also for the excited state. So some short range features are common, but others are not. If you talk about the Hall state or the ground state of carbon-12 displacement, the alpha clustering is still there, but the alpha clusters are. So it's an interesting idea. I don't know in practice how hard it is to implement it.
Yeah, nothing's ever easy in practice.
Okay, let's thank Jane once again. All right, our next speaker is Lovato from Argonne, and he will talk about hypernuclei with NQS.
Just I didn't want to repeat neural quantum state for the 10th time. It's like when I started this business, medium SRG was like everywhere, and at some point I got used to it. And anyway, not really. But anyway, so this talk is not as nice as the 2 previous ones. It's kind of embarrassing. And in fact, I shouldn't be the one giving the talk. Andrea Di Donna, a student in Trento, co-supported by STREAMLINE, is doing most of the work. And but he couldn't travel here for a couple of reasons. But when I'm presenting his work. So just one introductory slide. What is an hypernucleus? Is basically a nucleus in which you replace neutron with a strange particle. And in this work, we are considering lambda particles, single lambda hypernuclei. And there is a variety of experiments on the binding energies, and their properties are interesting for a number of reasons. And to me, they are very interesting for their astrophysical implications. If one thinks of compact objects like neutron stars, as the density increases, even if there is no interactions between protons and neutrons, we know that's not the case. But protons and neutrons are fermions. And so what happens is that they pile up in terms of their Fermi levels. And at some point, their pressure is not enough to stabilize a neutron star, but it gives you some pressure. And then it becomes convenient to form a lambda particle because it's distinguishable from protons and neutrons. So it will occupy a very low Fermi level, single particle state. And therefore, that will lead to a reduction of the energy and to the pressure of the matter. And in the early days, when people considered the formation of a Hyperon neutron star, they stumbled into this Hyperon puzzle, which is basically in one slide that I stole from Diego Leonardoni. I should credit him. Basically, the idea is that in the core of the star, the density is so high that it becomes energetically convenient to form Hyperons because they are distinguishable, as I said. But then what happens is that the equation of state becomes soft. So if you increase the density, you don't get a lot of pressure out of it, just because you can keep forming Hyperons. However, there has been a recent, very massive, more than 2 solar masses, neutron star observations. And in order to support such a mass, such massive neutron stars, you need a stiff equation of state. So somehow this contradicts the naive picture. I have Hyperons. I don't have enough pressure to sustain a 2 solar mass neutron star. How do we solve it? But when Diego was a postdoc here, what we did, we said, okay, let's start with a phenomenological Hamiltonian, 2 and 3 body forces. And then we can fit actually a repulsive nucleon-nucleon lambda interaction, 3 body force on existing data hypernuclei. These are S shell, P shell, and T shell hypernuclei. And this is our auxiliary field diffusion Monte Carlo calculations that we did. We tuned a very simple model of the coupling constant actually of the nucleon-nucleon lambda force. And we saw this basically. So this is the mass radius relation of a star. If you only include full nuclear interactions, 2 and 3 body, but then only 2 body lambda nucleon interaction, you get a very soft equation of state. If you're very far away from 2 solar masses neutron star, including an earlier parameterization of the lambda nucleon force, we could get something better, 1.2 solar masses. But then what we did by reproducing the energy of a bunch of light and medium mass hypernuclei, we were able to get, actually, with this parameterization specifically, this 3 body force is so repulsive that it never becomes energetically convenient to form Hyperons in the star, at least up to reasonable densities. Okay, then you can no longer really talk about nucleons, protons, and real explicit QCD degrees of freedom start playing a role. But that was a kind of, in the early days, it was completely phenomenological. Now we wanted to and the auxiliary field diffusion Monte Carlo had its own limitation. Okay, so what we wanted to do was to build on what we did on nuclei and try to extend it to hypernuclei. And here again, we start from the essential elements of nuclear binding. I really like this paper by Dean collaborators a few years back. I stole it shamelessly. But anyway, what we do, we start from in fact, Thomas gave me this suggestion years ago at the IMT, to be fair. And said, why don't you try a very simple interaction? And at the end, we tried it. And back then, we didn't include the projectors on the S waves, and it didn't work when I tried with you. But then including this makes the trick. So basically, it does the trick, because basically, this interaction is only effective in S waves, in even waves. And we fit there, it's inspired by binary CFT, but you cannot call it binary CFT because we're not taking the regulator to infinity. We're just fixing the coupling and the range of the interaction to reproduce the scattering length and the effective range in the S-wave scattering, neutron-proton, the neutron-proton channel. And then for the 3-body force, what we did, now this is a slight departure from what Bryce explained, is okay, again, it's a very simple 3-body force, very similar to what Dean is using, except that this one is local. It's a contact interaction in which we regularize the delta function as a Gaussian, and we can fit both the range and the strength by reproducing properties of light nuclei. And with Bryce, what we did, I mean, I like doing things by hand. I really painting and stuff. But anyway, so that worked fine. But then we said, can we do this more rigorously? And what we did, we said, okay, let's construct a full framework to be more rigorous and fit more nuclei. And so let's fit the binding energy of A equal 3, A equal 4, and also oxygen 16, as done in the Lovato, for example, potential. Let's try to assign a very small, I mean, an error bar, which is like 2.5%, I think, of the binding energy, something like that, just to see what we can do. And what we did, we basically trained a Gaussian, we computed a bunch of ground state energies for different samples of the regulator and the strength of the three-body potential. We trained a Gaussian process on it, and then we could do a Markov chain. We could sample these low energy constants and build these posterior distributions. We are not putting any prior on the low energy constants because this is not really an effective field theory. These are just distribution of based on the light. Okay? And here I'm showing the energy of oxygen 16, helium-4, helium-3, and Triton. We consider both Triton and helium-3 because we don't have, except Coulomb, we don't have the full charge-dependent and charge symmetry breaking terms. So it's either consider both or the average is the same thing. And then what we can do, you can get basically distributions for the range and for the repulsive, strength of the three-body force. This is what we got. This was like a kind of a warm-up problem because then we wanted to use the same machinery to fit hypernuclear forces. And this is what you get. This is basically a more updated version of Bryce plot, in which we're showing the energy per particle of a bunch of light nuclei up to oxygen 16. Blue is experiment, and orange is neural network quantum state. So the gray is what we use to fit. So oxygen up there and here, and the rest, if you want, is prediction. And that's basically it's the same pattern as before. Okay, we don't really gain much because there's only two parameters here. So what Bryce showed is exactly already what we knew was the case, but we slightly underbind the shell nuclei, as you can see, particular carbon 12. But we can do, I mean, the beauty of this method is that we can do any nucleus, open shell, closed shell, it doesn't really matter. And we always check at the end of the optimization that the quantum numbers are the one we expect. And they are always. But what we are, so again, this interaction works as Dean proved already. This works pretty well, but it has some shortcomings. And Bryce mentioned that we included charge-dependent terms, and Anthony here, he fit the different channels in the neutron-proton scattering. Sorry, proton-proton, neutron-proton, and neutron-neutron. So they distinguish these three. It improves a little bit, but it's almost negligible. What we're going to do next is to include P waves. And that will, we think it will change carbon 12, for example, and as it is observed. But we want to do that one step at a time. Try to find the minimal interaction that reproduces like nuclei well across the nuclear charts. Because mean field theorists do a great job, so I think there is some physics in there. But then let's go to the hypernuclear potential. We're using, again, a similar strategy. There is projector on spin-isospin channels. In fact, there is two spin-isospin channels. And again, we feed them to reproduce proton lambda scattering length and effective ranges, these two channels. Again, there's two parameters there, the range and the coupling constant. But then we have a three-body force, which is a little bit more complicated. This is lambda nucleon force. And there is three low energy constants, and we just keep one range for simplicity. And there are three channels that we have to fit. And in principle, three hypernuclei are enough to fit this force, but there is a lot of degeneracy between light hypernuclei, and the experimental data are not that accurate also. So what we did, we followed a similar strategy, and we decided to include a bunch of hypernuclei. I mean, in principle, these four are enough, but we also included oxygen 16 to remove some degeneracy. Okay. And as you can see, we repeated the same game. So we trained a Gaussian process we computed the ground state energy of light hypernuclei and oxygen 16 using either neural quantum states or the stochastic variational method. And we checked that for light nuclei, they agree, and they do agree. And then we, a stupid Monte Carlo sampling to sample the low energy constants of and the range of this potential based on the likelihood that we have. So here this is not a full Bayesian analysis because we're not putting any prior on the size of the energy constants and on the regulator. Okay, this is entirely driven by the experiments. But still, if one includes oxygen 16, we can constrain fairly well the range and the strength of the three-body force. And then this is actually the contour plots. This is the range of the Argonne nuclear force. And these are the three coupling constants in the three different channels. And it is very important to include oxygen 16 lambda to determine the range. If we didn't include that nucleus, then there is a degeneracy. Many potentials can reproduce equally well properties of light hypernuclei. But then again, we play the same game, say, okay, now we have this potential, it has been determined here and there, and you can try to reproduce the lambda separation energy. So what is the difference between the energy of the hypernucleus and the parent nucleus? And here we are comparing with some no-partial model and some lattice CFD calculations in purple, and no-partial model is in green. And we typically do fairly well. I mean, we compare this case, there is an uncertainty associated with the low energy constant and the range. But again, we are not including any truncation error or anything fancy like that. We are just propagating these experimental uncertainty in the determination of the lambda separation energy, which is not tiny. Okay, it's about it's around 2% of their values. Okay, so it's not crazily small like in nuclei. We didn't have to artificially increase it. But of course, a better analysis would entail including the truncation error of the theory and everything. Okay, this is just an exploratory study to see where we are. And again, we can reproduce fairly well. I mean, it's within 10%, the lambda separation energy of a bunch of hypernuclei. And it's not shown here, but we could do larger systems and it works fairly well. And again, this is open shell, closed shell. There is no difficulty. And again, we always check that the quantum numbers are the one that they have, after the fact, we check that the quantum numbers are the one that we expect. And then there is some physics, right? This was already physics, but there is something else. So the interaction between lambda and a neutron, or lambda and a proton, is attractive, but not as attractive as the proton-neutron, for example, or interaction. So here I'm plotting the single particle densities, so the probability of finding a proton or a neutron or the lambda particle from the center of mass of the nucleus. And this is helium-4 plus a lambda. Okay, so the proton and the neutron is basically on top of each other. There is only Coulomb. There is a tiny schema you cannot see. Here, what happens is that this interaction is not as attractive as the neutron-proton one, and so the densities are kind of more spread out. So the lambda particle extends outside of the nucleus. So if you think of the helium-4 nucleus, you have like a core of protons and neutrons, and then the lambda, of course, overlaps with the core, but leaks out somehow. And there, in independent particle pictures, they will all be in the S shell. And this is somehow what we see, even though there is no shell structure in our ansatz. It's the Faffian that Bryce mentioned, and I will come back to it. But then what happens if we do oxygen 16 lambda? Now I forgot the normalization of this density. I think they're normalized to unity. Okay, that's why you see the lambda density much larger than the other one. Now for oxygen 16 lambda, this is oxygen 15 plus a lambda. Okay, it's not oxygen 16 plus a lambda. That would be oxygen 17 lambda that we should show. I don't know why we didn't show it here, but here, what is the point is that in oxygen 16 at the mean field level, you have nucleons in the S shell, but also in the P shell, which it extends outside. But the lambda is a distinguishable particle, so it's always in the S shell, and it's basically inside oxygen 16. And this is something we do see. Okay, so the density profile of the lambda is inside oxygen 16 rather than being outside. Okay, this is a purely quantum mechanic. It's a manifestation of the Pauli exclusion principle. And if we did larger nuclei, say calcium 40, you will see lambda, you will see the density of nucleons to reach a flat value around here, but the lambda particle one will be very much inside of the nucleus. Okay, and I think this is a cool manifestation of quantum mechanics. And again, we don't use any shell parameterization. Everything emerges from the interaction. Just one slide on the architecture that Jane and Bryce have already explained, but I just wanted to show how we generalized it to deal with hypernuclei. The baseline is a Pfaffian Jastrow neural quantum states. So this is permutation invariant Jastrow and a Pfaffian. The Jastrow is a permutation invariant function, complex, and we typically limit for numerical stability, we limit the fluctuations of the exponential of the wave function from 10 to the minus 8, 10 to the minus 10 to the minus 8, 10 to the minus 8. And we use deep set to enforce permutation invariance in this Jastrow. Then the Pfaffian, they have already discussed it. What we do, though, that new here in a sense, is that hyperons are distinguishable. So what we can do really is to simply multiply the wave function of the hyperons and the antisymmetric function for the nucleons. So the X now denotes both the coordinates of the nucleons and of the hyperons, but the total wave function is just the product of the two. Of course, this is not general enough. What we do to make it more general is to add backflow transformations that are again inspired by, is based on the graph neural networks. So we iteratively build correlations. But the bottom line is that basically, instead of being X, Y, and X lambda the input to the Pfaffian and to the single particle orbital of the lambda, we do a backflow transformation. So actually, Xi depends on the coordinates of all the nucleons, and there should be a lambda here, and the coordinate of the lambda depends on the original coordinate of the lambda, but also on all the coordinates of the nucleons and of the lambda. Okay, so there is correlations in it. And yeah, this is pretty much it. So this is the first application of neural quantum state, strange systems. And we can claim that we distilled the essential elements of a nucleon binding, I think. And we combined Gaussian processes with neural quantum states just because it was very easy. It works out of the box and it was fairly cheap to compute a bunch of energies. The trick we did is that with neural quantum states, and Jane observed it already, is that, and Bryce as well. So suppose you train, you are given a set of parameters of your potential. You train the network, you get ground state energy. Then you want to explore a different set of low energy constants. Instead of starting from scratch, you start from a pre-trained network. And it basically converges in very, very few iterations. So it's very efficient to compute many realizations of the Hamiltonian. You don't have to start from scratch each time. Anyway, it is natural, as Jane said, to consider eigenvector continuation and parametric matrix models to treat larger systems where even this transfer learning becomes more computational intensive. And especially if we have more sophisticated interactions than this basically Gauss-based potentials. So we, with Andrea, we reached up to oxygen, basically A equal 20. But it's fairly easy to reach A equal 40 on Polaris, but we do need exascale resources to compute heavier nuclei. And these are more important for astrophysical applications, okay, because the central density is closer to the one that saturation density. And this formalism is directly applicable to study the onset of hyperons in neutron star matter. Now there is a catch here, of course, is that hyperons are supposed to appear in the high density regime, and we cannot use pi velocity in the high density regime by definition. Okay, so first we need to use high resolution interactions in our neural quantum state formalism, and then we can actually do this study. Okay, so that wouldn't really make much sense to study the onset of hyperons in the crust of neutron stars. Okay, okay, that's all. Thank you.
So questions? Okay.
Is there experimental data for systems with 2 lambda particles?
Yeah.
Have you compared with that?
No, we need to do. That's a good question. So that's in fact how you determine the lambda-lambda interaction. You can do either that on the lattice or use these systems. But we, in fact, the funny thing is that I don't know why, but Andrea wanted to design the ansatz so that you can put as many lambda particles as you want, but always ever use one. Because the lambda-lambda interaction is even, how can I say, less, it's even less constrained than the lambda n interaction, because they're, yeah, makes sense.
Yeah, I just have a physics question. There was some time discussing at Jefferson Lab to measure very carefully the hyper triton, the hyper helium, and so to figure out constants of the lambda n interaction, the low energy constant. Then there also have been proposals also to look at the hyperland.
Yes.
When I listen to you now, and I mean, the lambda is always in the S shell. Does it make then sense to even study the hyperland? To get some information, because you also find already out when you simulate the equation of state what the effect is.
Now that's an excellent point. So the story of that proposal gets personal, but I think there is physical sense. I mean, if you see the picture of here, for example, in lead, you would have basically completely flat from the nucleus up to here, and then so basically this is closer to what you have in infinite matter at saturation. So that's the rationale behind this experiment in lead. So the idea is that the environment itself is much closer to what you get in infinite matter than oxygen 16 lambda, for example. Okay, that was the idea behind it. To me, it would be nice to have an anchor point to make the best possible prediction, to constrain the lambda nuclear interaction on LIDAR system and then make a prediction for lead-208 lambda. And if that works, then try the neutron stars, rather than using lead-208 to constrain to something like history matching, rather than actually fitting the force of lead-208, because because otherwise it's a kind of cheating, right? If you fit really everything, then I don't know what kind of predictions you can make. But again, lead-208 would have a much flatter density, so it will be more similar to what is found in neutron stars.
So one is it's basically it's a magic cutoff or magic range that you're in. It's very finely tuned. That's why this lambda parameter was very sharp coming out. And that's somehow getting some E-wave physics that you need.
I think so. What I think it's happening, I think Dean explained it, but now I always forget the explanation. But I think what's happening is that you need to get the alpha particle right, so that you can get basically alpha cluster. Alpha clustering is very relevant, I think, within this interaction. In fact, you see it also. But then you need to get a little bit leaking out of it, not to get the collapse. And in fact, if we took a very short range for the three-body force, you can always fix, say, the alpha particles, right? But then what happens is that the strength of the repulsive term will be much larger, okay, because you have a narrower Gaussian but taller in a sense. But that doesn't give you enough repulsion in oxygen 16. In oxygen 16, you want a broader term because it scales like the number of triplets in a sense, right? And if it is too narrow, it's not effective enough. So you want to leak it. You want it to leak outside of the alpha particles. Basically, it acts like a cutoff in a sense.
Then a follow-up was from you. I also learned that non-locality was so important, but you don't have that. So how do I?
Our energies are not as good as theirs. If we could add a little bit of non-locality, I think it would improve it. But I didn't, by checking the numbers, I think we cannot do as well. I mean, we're doing okay, but not as really spot on, basically. And we don't. So,
one quick question. So now when you add lambda to oxygen 16, the neutron and proton densities, are they changed? Compare this oxygen 16, normal oxygen 16.
Yeah, so this is oxygen 15 plus a lambda. You can see that from here because the proton density is a little bit smaller than the neutron. Yes, that's right, because they are all normalized. So if you make it smaller here, you make it larger there. So this is why they're not the same. Neutron and proton are different. So this is 15 plus a lambda. Okay. But your question is, say, how do these densities change compared to oxygen 15?
Right. So basically that we
not much. I don't have the plot here, but I can show that to you. Not much. So the lambda, at least within this picture, they don't change much, but they change dramatically in some light hypernuclear, right? Some are not bound. It's the very presence of the lambda that makes them bound. For example, the neutron-neutron lambda system is bound, whereas the neutron-neutron is not. So if you were to compare the densities of neutron-neutron versus neutron-neutron lambda, it's dramatic, okay? So it acts like a glue. So it makes it more bound.
So in your helium-5 lambda, for the lambda distribution, there's a little bit of dip at the origin. Is that the 3 body force?
Yes.
Yeah, right there.
Oh, here actually, no, here I don't know. Sorry, I take it back. I thought you were talking about this. Sorry. The dip here is the shells, but it's also because of the three-body force. This one here, I'm not sure. I need to think about it. It could be also statistical.
Yeah, it's definitely in an S wave, but why would it dip right at the?
I think it's a study. I think the error bar sits underestimated here for some reason. It just shouldn't be a dip. I think it's purely a shell. This volume is also very tiny, so it's possible that we're underestimating the error of that point. I need to double check the statistical error.
Yeah, but there's not so many points right at the center. Yeah, we have the same issue. Our error bars are always much larger, right?
Yeah, so this is why I asked. He told me, okay, put like 20 million samples to this plot. That's invisible, but it's strange.
It's difficult to get short distance physics, right?
Yeah, exactly. Any other questions? If not, let's thank Ali once again. We'll take a break until 3:30 Central Time. Probably be closing the Zoom session until then.